So hello to everyone. Today, if there are no technical problems, I will explain to you what I have done this year as a research project. And okay, so if you don't see the blackboard, just say it to me. Okay, so as the title shows, I will speak about some properties of vector fields that are BV regular with respect to the space variable. And these vector fields arise in the context of fluid dynamics, and mixing is a behavior of a dynamical system. Okay. In particular, with Professor Bianchini, we addressed the question how many vector fields are mixing. Where how many is from the topological point of view. Okay, which means first, second category and density results. Okay, so I don't know if you know this kind of topic to discuss the size of a set. So I give the basic definition. So definition. We see the definition. Okay, we consider X and D a complete metric space. Complete metric space. Okay. Not the best idea to use this vector. Okay. We say that a set, a subset A of X is nowhere dense if the interior of the closure of A is empty. A set F is of first category if F is the countable union of AN, where AN are nowhere dense. Okay. So this definition, we see more or less. I will write here. Okay. Then a set of G in X is G delta if G is the countable intersection of open sets, and finally G is a residual G delta or a second category if ON are dense. So observe that we can give these definitions also in topological spaces, but in the hypothesis that we are in a complete and metric space, by their category theorem, the residual G delta G delta is dense, since it is the countable intersection of open dense sets. Okay, so it's clear. I don't know. Okay. So just to keep in mind, so example. So in the real line with the Euclidean distance, we have that Q is of first category, while the irrationals, is a residual G delta. So in literature, when you find the results that refers to genericity, you always have to find a residual G delta, which is a big set as irrational numbers, while a small set from the topological point of view is like Q, so a first category set. Okay, so this is how many from the topological point of view. Okay, now we have to understand which kind of vector fields we are considering. So, vector fields. For us are V, which is in with the time variable in 0, 1 times 0, 1 squared, which I will call K. So K is the unit square in R2, which are divergence free. So this is the symbol for divergence, and this is L1 almost every T, and it is the distribution of divergence. And B is in the space L infinity 0, 1 BB K. Okay, as Emanuele knows, these vector fields have a flow. So normally you can define a flow if you have a vector field which is Lipschitz in space and uniformly with respect to the time variable. But even if the vector field is quickly differentiable, you can give a notion of flow, and this is precisely what Ambrosio did following the Di-Fermat-Lyon theory. Okay. So in this case, there exists a unique flow xt from K to K with x which is continuous with respect to time and L1 with respect to space. And this flow has the following definition. It is called the regular Lagrangian flow. So this flow has the following properties. A, so for almost every x in the unit square K, x of t is an absolutely continuous integral solution of this classical V, gamma dot t equal V t gamma of t and gamma 0 x, so as a normal flow. Moreover, so thanks to the hypothesis on the divergence of the vector field. Thanks to this hypothesis, x of t is measure preserving for every t, which means that this flow, considered as a map, push forward the Lebesgue measure on the unit square is the Lebesgue measure. So sets with some measure are sent into sets with the same measure. Okay. And a powerful point of view is not just looking at the time evolving, so at the trajectories, but this time, if we fix the time, we fix t, we can look at the flow as a map from the unit square into itself, which is, so x of t goes from the square into itself, and it is an invertible map, and measure preserving, as I told you. And in particular, I call G of k the sets of these maps, like the flow, which are invertible and measure preserving. And this G of k is the group of automorphisms of the unit square. Automorphisms. So why it is a powerful point of view? Since in ergodic theory, they study the properties of automorphisms that preserve a measure. So indeed, this point of view makes a bridge between the theory of regular Lagrangian flows and ergodic theory. Okay, so the question was how many vector fields are mixing, so I have to speak about this mixing. Tell me if I'm not clear. Okay. Okay, we say that a map T, so mixing, what is mixing? So let's take T in G of k, the group of automorphisms of the unit square. We say that definition T is weakly mixing so notation Wm, if for every A and B Borel sets 1 over n, the sum from j from 0 to n minus 1 keep j of n perception with B minus the measure square tends to 0 as n tends to infinity. So this is Tj is the composition of j times of the map T, and T is strongly mixing if for every A and B Borel sets we have that T n of A intersection with B tends, as n tends to infinity, to the product of the two measures. Okay. So what is the meaning of mixing? So if you are, for example, in the unit square, and you have half of the unit square, which is made of milk, for the white part, while the gray part is coffee. And you want to understand fixed a set B. You have to imagine that A is, for example, the milk, so the white part, and B is the ball that I have drawn. And you want to understand when you mix something, what is the quantity of milk that you can find inside the set B. So you have to imagine that this milk, after mixing, is equally distributed in the unit square. So at the end, you expect that in B, half of the quantity is made of milk. So because it's you start from 1/2 milk and 1/2 coffee, you expect that in B you have 1/2 milk and 1/2 coffee. So at the end, the quantity of milk is 1/2 times the measure of the set B. Okay, so this is mixing, nothing more deep and so on. This is the definition. Okay, and we say that definition. So let B in L-infinity BB as the vector field we are considering divergence free. Okay, then B is weakly mixing or strongly mixing if it's a unique regular Lagrangian flow evaluated at time t equal 1, which is a map in G of K, the group of automorphisms, is weakly mixing or strongly mixing. Okay. So to apply the definitions, you simply have to extend periodically the vector field B. And so, if you call x at time t equal 1 the map T, then of course x at time t equal n is T composition n times. Okay, so this is the parallelism between vector fields and maps. So our question is, how many vector fields are weakly mixing or strongly mixing from the topological point of view? Okay, what can you find in the past literature? In the past literature, you can find just results for maps. In particular, these works are quite old and are especially from Almos, Oxtoby, Ulam, Katok, so varied mathematicians. Okay, so so past literature. Okay, if we take G of K, and in this space of automorphism, we put the L1 topology, so L1 topology. Then you have that in G of K, weakly mixing automorphisms are residual G delta. while strongly mixing automorphisms are dense, but they are a set of first category. So strongly mixing vector fields are like rational numbers, so a very small set, while weakly mixing are a very big set, like irrationals. And this is the result that you can find in literature. And our result is to reproduce the same for vector fields. And it seems logical, but it is non-trivial, since in general we don't know if an automorphism is generated by a vector field. So we have this big constraint that every automorphism should be generated by a vector field. Okay. So this is the past literature, and this is our theorem. So our theorem states precisely this fact. Okay. Theorem. Okay. So we consider so an infinity BB. Our vector fields, there are divergence free. Okay. With the L1 TX topology. Okay. Then there exists a set U that contains this space here. I omit always that they are divergence free, but they are always divergence free, such that U is a G delta set, and so it is a complete metric space by Alexandrov's theorem. Okay. There exists a good space containing the vector fields that are of our interest. Good means complete metric in order to apply the Bell category theorem. And inside U, weakly mixing vector fields, I call WMB, meaning the vector fields inside U are a residual G delta, while, as in the past literature, strongly mixing vector fields inside U are dense and of first category. Okay. So we hope to prove this result directly in this space, an infinity BB, but since we needed a complete space with respect to the L1 topology, we couldn't find estimates that made the total variation uniformly bounded for every vector field under consideration. So it was not complete, and for this reason, the trick was to enlarge a bit the space, this space here, in order to have a good space. So a G delta set, as Alexandrov theorem states, inside a complete metric space is still in a complete metric space. So it is a good space in which you can apply the category theorem, which is what is needed, as I told at the very beginning, to have that the countable intersection of open dense sets is still dense. So it's a residual G delta. So this is just a formal trick. This is space U, but the vector fields in L-infinity BV are dense in U. And in this space, we have the same result of the past literature. So weakly mixing are a residual G delta, and strongly mixing are a dense and of first category. Okay, if you are courageous, I can start with the proof of this theorem. So half an hour of proof. No, I will be smart.
But open sets are given sets, no?
The countable intersection of open sets is a G delta. But if they are dense, to have that the G delta is dense, you have to apply the category theorem.
No, I'm confused because you can open just one open set is a G delta set. How it can be a complete space?
No, I haven't understood the question.
I maybe didn't understand Alexandro's theorem.
No, so I so that it is quite confusing.
No,
but
because for me, if an open set is a G delta set in a metric space, it cannot be complete. I don't understand.
This theorem states that indeed a G delta set in a complete metrizable space is completely metrizable. So this is the theorem, and I don't know the proof of the theorem.
The generalization of Alexandrov to the Polish space is the same.
Yes, it's the same theorem. Indeed, if you have a G delta set in a Polish space, it is a Polish space. Okay, so we can start with the theorem, with the proof. And I hope that I was quite clear, since there's a lot of stuff inside. Okay, so there is an easy part. So easy part. Okay, we have to create this space U, and this space comes naturally from this definition. So we consider the method P going from L-infinity BV, which is contained in L1, into continuous function from 0,1 to L1 of k, okay, that associates with a vector field B. It's a unique regular Lagrangian flow. Okay. And this method P is continuous. And the continuity depends on a stability result on vector fields and regular Lagrangian flows, stability. And simply by continuity, there is a proposition that states that there exists U that contains L-infinity BV, G delta set, such that, and P tilde from U to the continuous function in L1, extension, so continuous extension. Okay, so this comes from several results that you can find in this book, Srivastava, a course on Borel sets, I think. So it is just a matter of metric spaces that when you have, sorry, I can the correct statement. So if you have a map that goes from a metrizable set space into a completely metrizable space, then you can always extend this map continuous to a continuous extension on a G delta set. And the G delta set, thanks to Alexandrov theorem, has always good properties. So it's a good space. And a comment on this result, one can ask, but in U, in general, you don't have a notion of regular Lagrangian flow, since you have that the definition is for this regularity of vector fields. But indeed, you can always define a flow, and you simply, if you take V in U, and you take some approximations of V in L1, you define the flow as phi tilde, the limit as n tends to infinity of phi tilde Vn. So you can always define a flow for this kind of vector fields. This is just formal, and it is not very deep, I think. Okay, so thanks to this result, we have that you have now this map to tilde. So phi tilde goes from U. It has always the L1 topology into continuous functions. A regular Lagrangian flow is always defined. So I compose phi tilde with the evaluation at time t equal 1, and I arrive precisely in this place in G of k, the set of automorphisms. Okay, now in G of k, we know that weakly mixing are a G delta. So they are the countable intersection of open sets for the moment. So weakly mixing vector fields are the counter image through a continuous map of this G delta. And so since it is continuous, it's still a G delta. So weakly mixing vector fields are still a G delta. So what about the residuality? So the density of these sets. The idea to prove the residuality is indeed the following. So claim, I do like to claim if strongly mixing vector fields are dense, since strongly mixing vector fields are also weakly mixing, so they are contained in weakly mixing vector fields, then if we show that they are dense, this weakly mixing vector fields is the countable intersection of open dense sets. It contains a dense, so every element of the intersection contains this set, which is dense. And thanks to the fact that U is a complete space, we have that by Baire category theorem, it's a residual G delta. So at the end, the only thing to really prove is the density of strongly mixing vector fields. Okay. finally, the only thing to prove are the density of strongly mixing vector fields. Okay, to prove this result, we proved an approximation result, which is this. Okay, so first approximation result, for every B in U, or in L infinity PV, since it is dense, for every B, for every epsilon positive, there exist two positive constants, C1 and C2, and there exists D in the natural numbers with D large as you prefer, and another vector field B of P such that B minus B of P in L1 Tx is strictly smaller than epsilon, and the total variation of B of P on K is lower equal than C1, the total variation of D plus C2. So for every vector field, we are able to produce another vector field B of P, which has this property that its regular Lagrangian flow, so such that its regular Lagrangian flow at time t equal 1 is a permutation of squares of size 1 over d. 1 over d. Okay, so I show to you the picture. So for every vector field B, we can build another vector field B of P, whose regular Lagrangian flow at t equal 1, so seen as a map, just send a square of the grid, that is the grid 1 over d, so the size of squares is 1 over d, and sends each square into another one. Okay, and this is a theorem which was inspired by the work of Shnirelman, and I explained to you the picture. It's clear, but so for example, this new regular Lagrangian flow during the time evolution shift the square 1 into the square 2, the square 2 into the square 3, and so on. So and the square 8 into the square 1. And I made with different colors the different cycles of a permutation, since as you know that every permutation can be seen as a product of disjoint cycles. So for example, you have this permutation. For example, you have this standard permutation 1, 2, 3, and 4 and 5. So these are 2 cycles, of course. And for example, you have 1, 2, and 3, and you have 4 and 5. So this is a permutation, and this is the permutation of squares in the unit square, so made of different cycles. And so this is our first approximation result, and I think that I don't have time to explain the idea of this result. But the second idea is doing another approximation result. So one has to keep in mind that when we have disjoint cycles of a permutation, we can always connect the cycles by transpositions. So, for example, if you had here 4 and 5, 3 and 4, 1, 2, 3, you have a unique cycle, a unique, you have this kind of picture, a unique cycle. So the second approximation result, is the following. So for every vector field B, for every B, there exists positive constants and dimension of the grid, and there exists this vector field BC such that its a regular Lagrangian flow at time t equal 1 is a unique cycle. Okay. So, for example, in the unit square, you have that this square goes into this square goes into this goes into this, and this comes back. And the power of this approximation result is indeed that you can control the motion of everything. Since you know at each instant of time, which is a multiple of 1, so each natural instant of time, you know the position of all the particles. Since you know that at time 1 this goes into this, then at time 2 it is here, and it is here. So you can control the motion at each instant of time. And so it is an easy motion. Okay, and the idea, so as I told you, is to connect the cycles that I drew in the picture, these different cycles, in a unique one. So how do you connect the cycles with the flows? Okay. So in the picture, I have drawn two cycles, C1 and C2, that I can draw here. So we have, for example, this cycle of squares, which is C1, and then you have another cycle, C2, which is adjacent to, so it is near to the other cycle. So the idea is that the transposition with flows can be done in a way that has to exchange the two squares. So this is the this first square, and this is the black one, the two. So how do you exchange between them these two squares with a flow? And the idea is the following. So the idea to exchange them is the following. Okay. So I consider this rectangle made of the two, and then I do a rotation. So I do this kind of motion, this rotation. So after an angle of 90 degrees, I have that 1, 2. After this rotation, they become, so you have to imagine this rotation, and it's 2 and 1. And then, not to complicate, to do complicated computations, we just do another rotation inside each one of these squares. So a rotation here and a rotation here. So it becomes 2 and 1. So they are exchanged, and it is precisely a transposition between squares with flows. And how to do the rotation flow? It's easy, but I think it's important to know it. So if you have this kind of potential, so V x1, x2 defined as the maximum between x1 minus 1 over 2 squared and x2 minus 1 over 2 squared. No. It's squared, it's outside. Sorry, I don't remember. It's outside. If you have this potential, then you define the rotating vector field R as the orthogonal gradient of V, which is by definition minus d, the derivative with respect to x2 and derivative with respect to x1. And then to get the flow, you have to compute R dot of t being equal to R of t. So this potential in the unit square, so in 0, 1 unit square, gives indeed this kind of motion. So particles do this kind of motion with this potential. Just a kind of Rubik cube in 2 dimensions. Okay, so this is the way to create a flow that rotates things into squares. And then we have to, of course, define this for rectangles and for small squares and for an affine, because this is for the unit square. So you have to change things a bit. So this is the idea for the second approximation result. And now that we have these 2 approximations, okay, the idea is the following. So we are able to have a motion which is very easy, since it is a unique cycle of squares, so not a complicated motion. And now to obtain a strongly mixing vector field, one moment. So, for example, we have this unit square. Okay. And now we have a unique cycle, which is, for example, I'm wrong. Well, so this is the motion. So this is a unique cycle of squares, so each one goes into the next one. So how to perturb B of C, so the vector field whose regular Lagrangian flow, it's a unique permutation, in order to have a strongly mixing vector field. The idea is to mix everything. So between, so imagine to have a mini beamer and you have the control of the motion. I don't know how to call the mini beamer. And then you mix at the interfaces between adjacent squares. So for example, you apply this mini beamer here, here, and here, here, and so on.
But the cycle is not made with the argument in the
It's not made with
the cycle. For instance, the 1 is exchanged with 2. 1 and 2 are not one with each other.
1 and 2 are not taken.
If you the first cube, and for instance, if you say that the PC is a vector field such that the flow exchange, put the first cube into a second cube, cube and that. But the numbering of the cubes are such that they are one with each other or not in general?
No, not in general.
Okay.
So, for example, this is just to understand the picture, but they can always go into another one and going back. So you have to choose, thanks for the question, you have to choose a precise enumeration. So because the idea is that you have to mix everywhere you can, just to mix the solution. You have to imagine that I have sets with different colors, and you have to mix them to create a mixed system. So you have to put this mini beamer everywhere. And this mixing method, this mixing flow, is well known in ergodic theory, and it's a flow that does this. It's called the folded Baker's method. Folded Baker's method. So like it's a panettiere. Because you have to, lo dico in italiano, dovete impastare, l'idea è di impastare l'insieme su se stesso, allargarlo e reimpastarlo. So the action of this map is the following, which is cut, rotate, and impastare. I don't know what to say. Folded.
No, just folded.
Okay. Okay. Thanks. And this is the action of this map repeated several times on these two sets. So at the end, after n going to infinity, you see that the two sets are well mixed. So, and this happens for every two sets. So it is just this map, and the idea is to apply this map so at the interfaces of squares, so which is precisely this idea. And for example, you choose an enumeration of squares, and then you mix the odd, dispari odd. I always confusing. The odd numbers with the next one, and then from 0 to 1 over 2 in time, and then in the rest of time you mix the even numbers with the next one, so the other interface. So at the end, every interface between adjacent squares is mixed, and indeed one can prove that with this kind of approximation you have a strongly mixing vector fields. So from a cyclic permutation, you can always generate a strongly mixing vector field. So I conclude from a cyclic permutation you can always generate a strongly mixing vector field. Okay, so this is the conclusion of the talk. 54 minutes. And I know that at the end I was a bit sloppy since it is quite technical, but the idea is that to have the density of strongly mixing vector fields, you have first to reduce your motion to a simple one through permutation, since you can control where squares go. And then once you have this control, you perturb it in an appropriate way. So you can perturb it also to have, for example, an ergodic vector field. So, and in this way, you generate a strongly mixing vector field. So thanks for your attention.
The definition of the
Well, I think that model sets are generated by open sets, so I think that you can check with the monotone class theorem to say if for open sets it's a monotone class, then to try to extend it to a sigma algebra containing open sets, but I have never tried them. So, but that theorem, I don't know if you know it, states that if you have a property for a class, which is a monotone class, then this property basically holds for the sigma algebra. So I think yes, maybe yes.
And then I have a question of the last part. You also love your story, you used to take the permutation.
Yes.
But I guess then in the very last part when you did the mixing of but I believe that it is closed in some sense, the cyclic permutation.
Yes, precisely the strongly mixing vector field that we build in this way is closed. So this is the cyclic one, this is the strongly mixing one, and you can find this estimate here. So they are closed in this topology, and moreover, the total variation of the strongly mixing is bounded. So it is in the correct space in U. So
if I do that in the stuff you were telling us, I still remain close.
yes, it's quite surprising because at the beginning I said how it's possible since you have to mix everywhere, but indeed you remain close. No, I don't have. But I mean, the vector field is long. This vector field is of 1 over d. Then you mix on squares, which is 1 over d squared. And so you have 1 over d cube.
Okay, so maybe the idea is that you mix not only on every level area.
No, you mix in the region, but I honestly I don't remember exactly the computation, but even surprisingly, because we have to deal with another parameter, then it comes
Okay, but the idea
out.
is not that the perturbation is vector if...
Because of course you see, it's the length of the vector field is b, is 1 over d, so it is the length of squares, and then you have to apply each square, we say, so it is 1 over d squared. And then for how many squares we have this? So for d squares, so it's d 1 over d cube, it's 1 over d, so it's small, because d, the dimension of the grid is large.
The naive idea is exactly the fact that you have
yes, because I mean, as I told, the length of the vector field is just the length of the side of the square. So you have this cancellation when integrating in the unit square with L1 norm. But thanks to this 1 over d, you can make it close to it. Yes.
Like in the, because you can do something similar also in the ergodic case.
Yes, in the ergodic case it's even easier. Of course, we have a strongly mixing vector field, so it is ergodic.
Okay. The question was just that.
But how to do it when you have a cyclic? So when you have this cycle, so this cycle here, and these are squares, then you apply the mini-primer only in the first square. So just to be more precise, things goes in this direction, but when passing in the first square, I say, you mix them. So at the beginning, at the end, you don't have an invariant set, since the only when you have this cycle, which are the invariant sets? For example, the invariant sets are these here. Since this set is sent into itself, so invariant set is TA equal A, and this set It's not a full measure. It's not nor 0 nor 1. So how to perturb this situation in order to avoid these cases? You mix here. So at the end, this ball is split by the folded Baker's map, and so you don't have these invariant sets. And the proof of this fact for ergodic maps is more easier than the strongly mixing. So it's just computation, and you see that it's ergodic. While for strongly mixing, you have to deal with the Markov processes. Quite obscure to me. Just another thing is that the residuality also for ergodic vector fields. So also ergodic automorphisms are a residual G delta, and also ergodic vector fields are a residual G delta. So and the proof is indeed this one, showing the density. Okay. Tell me.
I have a question about why we use the policy that vector field is infinity in time and the space, no? Because if I don't know if I'm wrong, but if you remember correctly that the work formats of the flow, all the vector field is L1 in time.
Yes, but Bianchini wants always to complicate things. So yes, we could just ask the L1 closeness and to consider with vector fields, but no, there is a precise reply to this. Since in another work of Alberti, Rippa, and Mazzucato, when they studied the mixing properties of flows, they required this L infinity in time property. So, of course, you can do this with weaker estimates, weaker requirements on the space. But since in this kind of topic they use this bound on the time, this L infinity regularity, we tried to do it in this regularity.
It's more detailed in L1, not
in L1, I don't know, you have the existence and uniqueness of the flow. Yes, so it's you stay in L1. No, it's not. L1, maybe yes.
Oh, L1 in time and DB.
L1 DB, no, it's the same. It's more easier, I would say.
And it's possible, another question, it's possible to give an idea, I don't know if you told about the best approximation result.
The permutations, yes.
How to move from that to the set permutation. Because you explained the second, no?
Okay, just as how to pass from a permutation to a cyclic one, just with transposition. Okay, so.
No, but the first one, how to pass to.
It is an hard point, and I can explain to you the first step, but if people want to leave, please leave. So the idea of this step, it's just a Shnirelman, but the point of Shnirelman is that it was incomprehensible. So no one understood this. And Shnirelman did the approximation result for maps. So it didn't require this BB regularity of the vector field, since in his approach this BB norm blows up. So we changed his proof. But the idea is the following. So you have to imagine to start from a map T. So you start from T. From T, or x of T at time equal 1, and you assume that T is close to the identity, enclosing C1 norm. So this is the first step of this proof. Then it's kind of using this step several times. Then what you can do is the following thing. So you have the unit square, K, and you have a T of K, and for example, lines of the grid are sent into these waves. Since it is close to the identity, and it is the identity on the boundary. The identity on the boundary. Okay. Okay, and I said, and I ask to find a grid in which rectangles goes into rectangles. Then to have squares into squares is more difficult, but the idea is from rectangles to rectangles. Then the idea is this. So you have this starting grid, which is, for example, 1 over n, the sides, and you consider these vertical lines here. And you do the counter images of these vertical lines at the beginning of the motion. The counter images are these lines here. Okay. So now what you do is the following. So start from this rectangle, and the point is that so consider just this stripe H1. And I ask, so for which alpha, this is H1, so for which alpha the rectangle of size alpha H1 is such that its measure alpha H1 is precisely the measure of this curved rectangle. So I want to find alpha for which this rectangle has the same measure of this curved one. Okay. So okay, I compute this measure. I know it since I know the map T, and the map is measure preserving. So I find this alpha such that this rectangle has the same measure of this curved one. And the idea is that, okay, so if I start from the rectangle of side alpha and 8 H1, here I do a flow, and this flow sends in a measure preserving way this into this. And this is the flow C of t. And this C of t has the property that sends horizontal lines into horizontal lines. You can do it. Giacchini for sure can do it. And so you reduce to a rectangle which has the same measure of this curved one. From the rectangle to the curved one, you apply a measure preserving flow. Then you apply the map T, and this map T, since it is the counter image of T, sends this into this one. This is the counter, so you take this. This is the counter image. From this, you can define a rectangle with the same measure. So you start from the rectangle, you perturb the rectangle to have the curved one. Then you apply the map T. The map T now rectify these lines here. And then what you do, so you arrive in this rectangle, you find beta such that the area 1 over n beta is equal to the measure of this rectangle here. Okay, so you do the same, but from the vertical point of view. So from this vertical one, this curved one, you do another flow that moves this in a measure preserving way into this with the size beta and 1 over n. So this is the basic idea. So whenever you have this map P close to the identity, you can always, if you do the composition, you have a new flow, sigma T. The sigma T is T, C of T, for T in 0, 1 over 2, and then it is eta T, T, and C 1 over 2. And if you do this composition, you have a new flow that at time 0 is the map T, and at time 1 it is a map that sends rectangles into rectangles. And so this is the basic idea. Then to apply it for flows, you have to recall that a flow, when the time is very small, so the flow close to the origin is close to the identity, since a flow which is x t of x equal to x plus the integral on the time of the vector field. So when the time is very small, this flow is close to the identity, and you can apply this approach. So this is the idea. Now I can kill myself.
Okay, so if there are no more